Hello students. So today we'll discuss the directive influence of the ortho-para directing groups. Okay. So here it is ortho-para directing groups. Remember that here all electron donating, or you may write all electron releasing groups. All electron donating or electron releasing groups are example of the ortho-para directing groups. See, some examples of electron releasing groups are like OH group, like alkyl group, like alkoxy group, like NH2 group, etc. These all are the electron releasing group. And remember, these electron releasing group, they exhibits plus I effect and plus M, or you can say plus R effect. Is it clear? So what happens here? These electron releasing group, due to their plus I effect and plus R effect, they increases the electron density over the benzene ring, means increases the electron density in the cloud which lies above and below the plane of the ring, and that's why they makes the ring more susceptible for the electrophilic attack, and thus these electron donating groups are also called ring activator, because they increases the electron density over the ring. Is it clear? Here we'll explain this ortho-para directing effect of the OH group. Is it clear? See, let this one is a benzene ring and here it is a OH group. See, in this one is the phenol. Here the oxygen is having a two lone pairs, and see the electron pair, this lone pair is in conjugation with the ring. See here, double bond, single bond, double bond, single bond, and lone pair. Wherever the lone pair lies in conjugation with the double bond, so these electron pair, a lone pair, will participate in the resonance. See what happens here? This electron pair shifted in the forward direction, and now this carbon will become pentavalent. So simultaneously these pitrons will shift to the next carbon, and we'll get another resonating structure. Here these two double bonds remains as such. As the pitrons of this bond shifted over this carbon will become electron rich and negative charge. Now here in between the ring and oxygen, a double bond will arise. See, as oxygen has donated its electron pair, so that's why will become electron deficient and there will be a positive charge over it. Now, in order to minimize the stress, see this electron pair will shift in the forward direction. Now this carbon will become pentavalent. So simultaneously the pitrons will shift to the next carbon and we'll get another resonating structure. See here, double bond. As these two electrons shifted here, double bond will form. This carbon will become electron rich and negative charge. Here there's the double bond, oxygen there over H, only one pair of electron and positive charge. Again, these electrons will shift in the forward direction. Now, this carbon will become pentavalent. These pi electron will shift in the forward direction. Again, we will get another resonating structure. Here, there is the double bond. As these two electrons shifted here, double bond will form here, and this carbon will become electron rich and negative charge. Here, there is the oxygen, which bears partial positive charge. Now, these two electrons will shift in the forward direction in order to minimize the stress. This carbon will become pentavalent. Now, these electrons will shift over the oxygen and we'll get another resonating structure. Here, double bond, double bond. As these two electrons shifted here, double bond will form here. Now, single bond will left in between the ring and oxygen. And now, at the oxygen, there are two pair of electrons. These are the possible resonating structures for the phenol. Actual structure is none of these. Actual structure lies in between of all these possible structures. Here, in actual structure, the negative charge rotates over the ring, and in between the ring and OH group, this carbon-oxygen bond bears a partial double bond character. And at the oxygen, see here, if you analyze these possible resonating structures, you will find that this phenolic oxygen bears positive charge. So, this will have a partial positive charge. This one is its actual structure, or you may call it as a resonance hybrid. See, as we know here, we must start numbering here from the carbon at which a substitution occurs. Means we'll count the carbon at which there is the OH as number 1. Now, starting numbering from this carbon, this is 1, this will be 2nd, 3rd, 4th, 5th, and this one is 6th. See, now analyze these resonating structures for the phenol. You will find that the negative charge is either at position 2 or position 4 and position 6. See, means negative charge arises at position 2, 4 and 6. It means, see, due to presence of electron cloud over the ring above and below the plane of ring, this ring becomes susceptible for electrophilic attack. Now here, as due to since here the electron releasing group is there, so it will release the electron, and as a result the electron density over these three positions 2, 4 and 6, this increases. So that's why these three sites 2, 4 and 6 becomes more susceptible. So these sites, they becomes more susceptible for electrophilic attack. Means we may say that the electrophile will attack at position 2, 4 and 6, while we are forming the di-substituted product from the mono substituted product. And as we know, the position, or you can say the site 1, 2 and 1, 6, they are identical. This is already discussed in previous video, and this is called ortho position. And similarly, the site 1, 4 is called, a para position. It means if the substitution occurs either at position 2 or 6, so this one, the substituted product, will be called ortho product. And if the substitution occurs at position 4, that will be called the para product. Is it clear? See, and see here this electron releasing group, they are increasing the electron density over 2, 4 and 6, and that's why these electron releasing group or orthopolar directing groups are also known as ring activator. Okay.